Hello everyone. My name is Dr.E.Purushotham, Professor of Physics, Department of Basic Sciences, School of Sciences and Humanities. A warm welcome to today's video lecture, that is Law of Universal Gravitation. So coming to what is the why the law of universal gravitation is important. So gravity's rule, yes. So these are used in the gravitational law is used in the gravitational law is used in computer graphics, and it is also used in satellite computing, artificial intelligence and machine learning, IoT, sensor networks and mathematical modeling. What is the law of universal gravitation? Every particle in the universe attracts with other particle. Every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This force acting is along the line joining the two particles. So, what I am saying here, this force F1 or F2 in general, every particle attracts every other particle in the universe with some force F. The F is directly proportional to the mass of two particles M1, M2, the product of two masses, and inversely proportional to square of the distance between them. So F1 is equal to F2 is equal to F. F is directly proportional to M1, M2 and inversely proportional to square of the distance between them. So proportionality constant, that is capital G, remaining M1, M2 by that distance square. So try to see here, every particle in the universe attracts with the other particle. The force F is directly proportional to the product of two masses M1, M2 and inversely proportional to square of the distance between them. So F is directly proportional to M1 into M2, inversely proportional to square of the distance between them. So we can write F is directly proportional to M1, M2 by R square. Proportionality constant capital G, F is equal to capital G into M1, M2 by R square. F is equal to G. For example, other mass at the place of M1 take small m, at the place of M2 here take small m, here capital M. We can modify F is equal to G small m into capital M by that distance square. You can see equation 1, where M1 comma M2 are two massive particles and G is the universal constant. The capital G is the universal constant. That value is given by G is equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square. So G value does not depend on nature of the particle and nature of the medium. Its value is same anywhere in the universe. Hence, it is called universal gravitational constant. Universal gravitational constant. Why is G called capital G called the universal gravitational constant? The capital G is known as universal gravitational constant. What is the reason? So its value remains the same everywhere in the universe. So try to understand here the point. G is called the universal gravitational constant because its value remains the same everywhere in the universe. Unlike many physical quantities that change with the nature of the materials or the surrounding medium, the value of G, capital G, does not depend on the type of objects involved, their composition, size, or the medium in which they interact. It is a fundamental constant of nature that governs the gravitational force between any two masses. From this explanation, since capital G has the same value in all regions of space, on Earth, in stars, on other planets, and even in distant galaxies, it is termed universal. This constancy makes it a foundational constant in the study of gravity and helps us apply Newton's law of gravitation to the entire cosmos. Therefore, because its value is independent of the nature of particles, the medium, and location, G is rightly called the universal gravitational constant. Problem on universal gravitational law. Two small metal spheres, each with M1 is equal to M2 is equal to 2 kg, are placed on a smooth table in a physics lab. The distance between their center is 30 centimeters. A student is curious to find the gravitational force of attraction between them due to their masses. Given that the universal gravitational constant 6.67 into 10 to the power minus 11 Newton meter square, calculate the gravitational force acting between two spheres. So, what is capital R, smaller distance between two masses? 30 centimeters. 30 into 10 to the power minus 2 meters. So, given G value 6.67 into 10 to the power minus 11 Newton meter square per kg square. Applying this all in the principal formula, F is equal to G M1 M2 by R square. So 6.67 into 10 to the power minus 11, 2 into 2 by 30 into 10 to the power minus 2 whole square. So trying to see here, given M1 2 kg, M2 2 kg. So distance 30 centimeters, 30 into 10 to the power minus 2, that is 0.3 meters, and G value also given here. So applying all the values here, we get 2.964 into 10 to the power minus 9 newtons. Coming to another formula, another problem. So in physics experiment, two electrons are placed zero point 0.5 centimeters apart in a vacuum. Each electron has mass of 9 into 10 to the power minus 31 kg. A student is curious to calculate the gravitational force of attraction between the two electrons using the universal gravitational constant. G is equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square. Help the student determine the gravitational force acting between them. So given values, M1, mass of electron 9 into 10 to the power minus 31 kg. So M2 is the same 9 into 10 to the power minus 31 kg. Distance given zero point 0.5 centimeters, that is in meters, zero point 0.5 into 10 to the power minus 2 meters. 1 centimeter is equal to 10 to the power minus 2 meters. G 6.67 into 10 to the power minus 11 Newton meter square per kg square. So the formula we know very well. The force of attraction between two particles F is equal to G m1 m2 by d square. Substituting this is G value, this is m1 value, same m2 value, and the distance square. So after calculation, we get 216.108 into 10 to the power minus 68 newtons. Coming to the relation between acceleration due to the gravity small g and universal gravitational constant capital G. So you try to understand here. Let us take a planet like Earth. This is the Earth. So this is the center. Capital M is the mass of the Earth. Capital R is the radius of the Earth. So on the Earth, let us take an object. So between these two attractional forces F, the mass is M. M is the mass of the object. Capital M is the mass of the Earth. Capital R is the radius of the Earth. So the force of gravity due to the Earth is weight of the object on Earth, which is given by F is equal to mg. That is equation number 2. What about equation 1? The force of attraction between the object and Earth, that is G, small m, capital M by the radius square. So this is equation number 1. From equation 1 and 2, we can write. So this is equation 2 is equal to equation 1. So equation 2 F is equal to mg. Equation 1 g m by r square. So small m gets cancelled. Remaining small g is equal to this g into capital M by r square. So this equation is known as the relation between small g and capital G. And also we can write from this relation capital G is equal to capital G is equal to small g capital R square by capital M. This relation is also known as the relation between small g and capital G. Small g value changes from planet to planet. It depends on mass of the planet or Earth and capital R of the planet or Earth. So this is the relation between small g and capital G. So coming to one example problem, a astronaut is conducting an experiment on the moon and wants to calculate the moon's mass. He knows that the acceleration due to the gravity on the moon's surface is 1.67 meter per second square, and the radius of the moon is 1.74 into 10 to the power 6 meters. Using the universal gravitational constant, same 6.67 into 10 to the power minus 11 Newton meter square per kg square. Help the astronaut calculate the mass of the moon using the gravitational formula. So the formula is given by the relation between small g and capital G. So given value G value 6.67 into 10 to the power minus 11 Newton meter square per kg square. So you know very well the moon small g value is equal to capital G mm by r square. So radius of the moon. So what is the radius of the moon? 1.74 into 10 to the power 6 meters. The mass of the moon, capital M. Mass of the moon, what is that? So moon mass 1.67 into what is that? So we need to calculate the Mass of the moon. Mass of the moon. The moon acceleration due to the gravity gm is equal to 1.67 into 10 to 1.67 meter per second square. Substituting all the values here, gm r square. So from this relation, gmm by r square, we know very well the relation between small g and capital G. So this is moon gm, capital G same, mm by rm square. So substituting all the values, acceleration due to the gravity on the moon 1.67 meter per second square, radius 1.74 into 10 to the power 6, so square square. So G value 6.67 into 10 to the power minus 11 Newton meter square per kg square. So after calculation, the mass of the moon 7.58 into 10 to the power 22 kg. So daily life examples of acceleration due to the gravity. You have been observing in your daily life. So a ball falling from your hind accelerates downwards due to the small g, acceleration due to the gravity. A freely falling body having some acceleration is called acceleration due to the gravity. Raindrops falling gain speeds as gravity pulls them down. So next you see here a person is jumping, comes back to the ground because the acceleration due to the gravity pulls them downward. A stone dropped into well accelerate as it falls due to the acceleration due to the gravity. An apple falling from a tree is a classic example of small g. Water flowing down a slope is guided by Earth's gravitational acceleration. Objects slipping off a table fall to the ground because of acceleration due to the gravity. A car rolling downhill accelerates mainly because of acceleration due to the gravity. A skider falling down gains speed due to the small g before reaching terminal velocity. So, coming to applications of acceleration due to the gravity. Using the acceleration due to the gravity, we can design of buildings and bridges. So, engineers must consider the gravitational pull acting and every part of the structure. The weight of beams, floors, people, and equipment is calculated using the acceleration due to the gravity. This ensures that buildings and bridges can support loads safely without collapsing. So, coming to this projectile motion calculations. Whenever a ball, arrows, stone, or bullet is thrown, its curved path is determined by acceleration due to the gravity. Gravity. Gravity pulls the object downward, shaping its trajectory. Without understanding G, predicting where objects will land would be impossible. So, designing elevator systems. So, simply elevators accelerate upward and downward. Engineers must consider acceleration due to the gravity to calculate counterweight balance, motor power, braking force, and passenger safety. Pendulum clocks also working on depending on small g. The time period of a pendulum depends on directly on the value of small g. The clocks using pendulums are adjusted according to gravity at different places on Earth to keep accurate time. Accurate time. So roller coaster design, fluid pressure calculators. So pressure in liquid increases with depth because of the weight of the water above. This pressure is calculated using pressure P is equal to H rho g, height, density, and small g acceleration due to the gravity. Engineers use this to design dams, tanks, reservoirs, and submarines, spacecraft launch and re-entry. The escape of Earth's gravity, rockets must overcome the force determined by using G. The required energy, thrust, and speed, that is, the speed means escape velocity, are all based on the value of acceleration due to the gravity. Design of weighting missions. A weighing mission works by measuring force since weight is W is equal to mg, we know very well. M is the mass, G is the acceleration due to the gravity. The mission uses G to convert force into mass. Without small g, acceleration due to the gravity, weighing devices would not function accurately. So civil engineers also used the acceleration due to the gravity in dams, canals, slopes, structures like that is the dams, canals depends on gravity driven water flow. Gravity fed water system, sports science, everything the small g is used. So architecture and design, physics experiments also we are using, aviation and everything, medical bio mechanism also the small g is using. Gravity affects how we walk, run, stand and balance. The blood pressure in our legs and the momentum of body fluids are influenced by acceleration due to the gravity. Doctors and biomedical engineers use this knowledge for observing exercise and using scientifically. So vehicle safety system also they are using, earthquakes and vibration analysis, irrigation and agriculture related, these are used. Some examples of universal gravitational constant. The earth pulling off downward, the gravitational force uses capital G. The moon causing tides, the earth moon gravitational force is determined using capital G. A satellite, planets orbiting the sun, a car parked on the road, weighing on object on a weighing mission, a pendulum working, everything the G is influencing. So applications of capital G. So calculating gravitational force between any two masses, the capital G is compulsory. We are using. Using Newton laws of gravitation, universal gravitational constant allows us to find the force between planets, stars, and even small objectives. Determining the weight of the object, weight mg, and g itself is derived from capital G. Thus, capital G indirectly determines how heavy objects feel. Studying planetary motion, Kepler's laws, and orbital calculations depends on capital G to determine how planets orbit the sun. Satellite launching and orbiter design. Engineers use capital G to calculate the gravitational pull that keeps satellites in stable orbit around Earth, predicting the motion of moons around planets. The attraction between planets and their moons is computed using the universal gravitational constant. Calculating escaping velocity depending on capital G. So finding mass of planets and stars using the capital G. So using the capital G, we can understand tides. Tides occurs due to the gravitational pull of the moon and sun calculated using universal gravitational constant. Space mission planning. So explaining free fall motion and gravity near Earth with the relation small g is equal to gm by r square. This formula uses capital G. So the gravity we feel on Earth is derived from universal gravitational constant. Determining the orbital period of planets, studying the black holes also using capital G. The immense gravitational force of black holes is calculated using the universal gravitational constant to understand even horizons and mass. So, understanding the galaxy rotation and structure, astrophysicists use G to analyze the gravitational pull with galaxies and clusters. Formation of stars and planets. So gravity pulls gas and dust to form stars and planets. This gravitational attraction is explained by using universal gravitational constant. Modeling the expansion of the universe. Cosmological models use G in Einstein's field equations to understand the universe's evolution. Earthquake science, geophysics. So gravitational measurements using capital G help map density variations beneath Earth's surface. Everything we can calculate using the universal gravitational constant. So design artificial gravity environments, mass density calculation of Earth's, understanding motion in binary star system, everything we are using capital G. So, what is the distinction between acceleration due to the gravity and universal gravitational constant? So, you know very well, small g is equal to g m by r square. Capital G is equal to gr square by m. Small g represents acceleration due to the gravity. Capital G represents the gravitational constant. Acceleration due to the gravity value G is equal to 9.81 meter per second square. So universal gravitational constant value 6.67 into 10 to the power minus 11 Newton meter square per kg square. The small g value changes planet to planet. Capital G is universal constant. G depends on mass of the planet and radius of the planet. Capital G does not depend on any factor or physical quantity. Yes, G, small g, differs from planet to planet. Capital G is constant. So, acceleration due to the gravity small g affects the weight of the bodies. Capital G affects gravitational force between two masses. G can be measured with simple apparatus. Capital G needs highly sensitive experiments. So, acceleration due to the gravity changes with latitudes. G is independent of latitude. G is maximum at poles. G is the same at pole and equator at any place. G depends on local geological conditions. Capital G does not depend on geological conditions. So, acceleration due to the gravity small g represents gravitational field intensity. Capital G appears in Newton's gravitational formula. Small g is the vector quantity and capital G is the scalar quantity. Scalar quantity. So G is the acceleration due to the gravity. Capital G is the universal gravitational constant. So G varies, small g varies from place to place. Capital G remains the same everywhere. G depends on mass and radius of the planet. G does not, depending on any physical quantity. So G changes altitude. Capital G is altitude independent. So small g value decreases with depth. G does not change at any place. So small g affected by Earth's rotation. Small g is unaffected by rotation. So g is a derived physical quantity. G is fundamental physical, capital G is a fundamental physical quantity. Small g has relatively large value 9.8 meter per second square. Capital G has a very small value 6.67 into 10 to the power minus 11 Newton meter square per kg square. So small g values meter per second square, capital G values, uh, small g has units meter per second square, capital G units Newton meter square per kg square. So you can see here another distinctions. Small g is the direction is towards the center of the earth. Capital G has no direction because of it is a scalar quantity. The small g is used equations of motion near earth. Capital G is used in universal gravitational calculations. Small g determines how fast objects falls. Capital G determines gravitational attraction strength. G varies over mountains and valleys. G stays constant at any place. So, small g influences pendulum time period. Capital G does not affect pendulum motion. So, small g influences escape velocity on planet. Small g is Earth specific unless otherwise stated, but g is always constant. Yes. What I am saying here, the acceleration due to the gravity influences escape velocity on planets. The universal gravitational constant influences universal gravitational force. Small g is Earth specific unless otherwise stated. G is universal for all bodies. You see here, small g affects the projectile motion and their trajectory. Capital G, you try to understand here, does not directly affect projectile motion. So, acceleration due to the gravity small g determines terminal velocity of objects. G does not, the capital G does not influence terminal velocity. Small g value varies slightly due to the temperature of Earth's crust. G does not depend on the temperature. Acceleration due to the gravity small g affects pressure at a depth in fluids. Capital G, universal gravitational constant, does not affect fluid pressure directly. So you try to understand the small g is part of gravitational field equations, but capital G is not part of force equations. Small g, acceleration due to the gravity, is influenced by the Earth's density distribution. Capital G is unaffected by density distributions. So acceleration due to the gravity measurable at any point on a planet's surface. G is constant in all measurements. Acceleration due to the gravity small g determines the curvature of natural paths near Earth. Capital G determines force between celestial bodies. Acceleration due to the gravity is used in biomechanisms, that is walking, jumping. G is used in astrophysics. So you see here, the small g affects the atmospheric thickness. Capital G does not affect atmospheric directly. Small g value changes in elevators with the operant weight. G has no effect on operant weight changes. Acceleration due to the gravity varies due to the Earth's flattening. G is unaffected. So small g influences tides indirectly. Capital G governs gravitational attraction causing tides. Small g depends on the particular celestial object. Capital G applies equally to all celestial bodies. So acceleration due to the gravity is different on Earth, Moon, Mars, other places. Capital G value is the same at any place on Earth, Moon, Mars, etc. G can be altered in artificial gravity experiments. Capital G cannot be altered by any artificial experiments. So small g value is essential for orbital mechanics near Earth. Capital G essential for universal orbital mechanisms or mechanics. Acceleration due to the gravity affects structural engineering calculations. Capital G, universal gravitational constant, does not influence structural design directly. So, acceleration due to the gravity, small g, impacts sports physics, that is, jumping, height, throw, distance, etc. But universal gravitational constant, capital G, has no role in sports physics. Small g value is larger and massive planets. Small g, capital G value is very small. G is useful to calculate gravitational potential near Earth. Capital G is used to calculate universal gravitational potential. So, this small g describes local gravitational conditions. Capital G describes the universal law of gravitation. Acceleration due to the gravity influences fluid flow in open channels like rivers. So, universal gravitational constant, capital G, has no role in fluid flow dynamics. Small g value changes slightly with seasonal mass redistributions, ice melt, ocean shifts, etc. But universal gravitational constant capital G remains unaffected by seasonal or environmental changes. Small g acceleration due to the gravity affects the buoyant force experienced by objects. Capital G does not influence buoyancy. So acceleration due to the gravity can vary due to Earth's internal mass movement, that is called magma flow. The universal gravitational constant capital G stays constant regardless of internal planetary processes. So coming to the summary, Newton's law, we know very well. Here you can see a force. The attractional force F is equal to G into M1 M2 by R square. You try to see here the Newton law. F is directly proportional to M1 M2 by R square. The proportionally constant capital G. The G is equal to 6.67 into 10 to the power minus 11 Newton meter square kg square per kg square. We clearly explained in this video. So it is also known as the universal gravitational law is known as Newton's law of gravitation or inverse square law of gravitation. So inverse square law of gravitation, force is inversely proportional to square of the distance between them. Doubling distance, we get force by 4. We discussed acceleration due to the gravity. G is equal to gm by r square. So small g value 9.8 meter per second square near Earth. Also, we discussed in this video clearly. What are the effects? The planetary motion, satellite orbits, tides, space navigation, effects we discussed. And also clearly we discussed the distinctions between acceleration due to the gravity small g and universal gravitational constant capital G. So especially for CSC relevance related physics in simulations, GPS algorithms, artificial intelligence in astronomy. Also, we discussed in this video clearly. Acceleration due to the gravity, daily life examples, applications, the universal gravitational law, daily life examples, applications, and the distinctions between acceleration due to the gravity and universal gravitational law also clearly we discussed in this video. Thank you. Thank you so much. Thank you.